Hi, I am Sanjay Patel. We have defined the concept of sequence mathematically in our previous video. We also have learned special classes of sequences like monotonic sequence, bounded sequence, and so on. Now in this video, we want to understand very important concept about sequences, and that is the concept of limit of a sequence. This limit of a sequence concept is very useful in defining convergence and divergence of infinite series. So these are all our prerequisites we are understanding in our first two videos. So let us consider a particular sequence to understand the concept of limit of a sequence. So let me take an, some sequence, one particular sequence, say 1 upon n. This is the given sequence, okay? Be a given sequence. And then we can generalize the meaning of limit of a sequence. This sequence 1 upon n, the terms are 1, 1 by 2, 1 by 3, 1 by 4, and so on. The 10th term is 1 upon 10, and so on. So what is our objective here is we want to understand that all these terms, this is the first term, say a1, this is a2, this is a3, this is the 10th term, a10. All these terms, does it approach to some fixed real number or not? Means if you keep on increasing the term number, that is 2, 3, this n, if you keep on increasing n, then does this an goes to something, or does an approaches to some real number after some stage? So here we can observe that these values keep on decreasing. For example, this number 1 by 2 is 0.5, this is 0.5, a3 that is 1 by 3 is 0.333 and so on, a10 that is 0.1, and if you take 100th term, that is 1 upon 100, this is a 100, and the value of this is 0.01. So it seems that all these terms of the sequence approaches to a real number 0. And this we want to verify mathematically. Means if you keep on increasing the value of the subscript n, this term number n, then this an is going near and near to the number 0. This situation, this number 0 is called limit of this sequence. Let us understand whether it is actually approaching, or can we make an closer and closer to 0. The question is how much close you can take the terms an to the number 0. Means if you see the 100th term, or say 10th term, the 10th term and the difference between 10th term and this fixed number 0, let me write this number as a. So difference between the 10th term and the number a, that is a10 minus 0, is 0.1 minus 0. So the difference is 0.1. If you take the 100th term, then the difference a100 minus a, that is 0.01 minus 0, is equal to again 0.01. So this distance between the terms an and the number a, that is an and 0, is becoming smaller and smaller. Then our question is how much small you can make the distance. Can we make this distance or this difference less than a given positive number, and any positive number, and that arbitrary positive number we denote by the symbol epsilon. So if epsilon is any say positive small number, then my question is, can we choose the term number n so that after that term onwards, the difference between the term an and the number 0 can be made less than the given epsilon, where which is epsilon is a very, very small number. Okay, so question is, given any small number, let me write properly. So the question is, given any small positive number epsilon, okay, epsilon that is always positive, can we make can we make the distance or the difference between an and a less than epsilon? That is, can we make mod of an minus 0 less than epsilon? So this is our main question. So what should I choose as the value of n so that the difference between an and 0 is less than the any given small positive epsilon? This we can think in this manner. An minus 0, that difference is less than epsilon. That is, an is 1 upon n, minus 0 is less than epsilon. So that means we have to do mod of 1 upon n less than epsilon, or you can say, which is same as 1 upon n less than epsilon, because n is positive, n is a natural number. So 1 upon n is less than epsilon. And that gives us n, if you take the reciprocal, you get n is greater than 1 upon epsilon. So in order that this condition is satisfied, we should choose the value of n to be greater than the number 1 upon epsilon. Okay. And remember, we want the term number n for which an minus 0 is less than epsilon. So that term number must be always positive integer. Okay. So if I consider, say, epsilon is equal to, if I take epsilon is equal to, say, 1 upon 11, which is also a small number, okay, greater than 0, then n greater than 1 upon epsilon means n is greater than 1 upon 11, means n is greater than 11. That means if you want to make n minus 0 less than epsilon, then you should choose the value of n to be greater than 11. That means the term number must be greater than this 11. So this number 11, we'll call it as, say, small n, or say n0, whatever. Okay. So this means if you choose n greater than m, then an minus 0 will be less than epsilon is equal to 1 upon 11. So in general, what can be taken as the value of m that we want to understand? Remember, here I have taken epsilon is equal to 1 upon 11. But if I choose some other number, say, if I choose epsilon is equal to, say, 2 greater than 0, okay, then n greater than 1 upon epsilon, that means n is greater than 1 upon 2, and that is nothing but 0.5. So this says that the term number n you must choose greater than this real number 0.5. Okay, so what I want is some term number which is integer. So I cannot take 0.5 as my term number. I must choose some integer which is greater than this 0.5. So what I will do is I will choose the first natural number, because after 0.5 the first number occurs, which is positive integer, is 1. So that means if you choose the term number greater than 1, then you have this an minus 0. Means if you choose n greater than 1, then the difference an minus 0 is less than epsilon is equal to 2 in this case. So in general, an minus 0 is less than any given epsilon, if and only if n is greater than 1 upon epsilon. But this 1 upon epsilon, I cannot take as my term number. So what should I do is I should take a positive integer after this 1 upon epsilon. How that can be done? See, if you add a 1 to this, because 1 upon epsilon can be 0 point something, or it can be some integer, as you have seen in this particular cases. So what should I do is I must choose that number, this number which is required here. In this case, it is m is equal to 1. In the previous case, it was m is equal to 11. Okay, here m is equal to 11. So if we take say m is equal to, say, the bracket 1 upon epsilon plus 1, this is called box function. It means it is the largest integer which is not greater than this number. The meaning of a square bracket x, or the bracket function, or a box function, is it is the largest integer largest integer, okay, which is not greater than x, which is not greater than x. So it is less than x, okay, or less than or equal to x, because x can be integer. So if you have say bracket of 1.5, then 1 is the largest integer which is not greater than 1.5. If you take 1.001, then again the value is 1. So on the number line, whatever the number you choose, say if I take 1.999, okay, then the largest integer which is not greater than this real number x is always on the left hand side. Okay, so we have to choose the nearmost integer on the left hand side of the number x, and that will be the largest and not greater than the number x. So if you have minus say 2.3 for example, then minus 2.3 will be somewhere here, and on this side we have minus 2 and on this side we have minus 3. So minus 3 is the integer on the left hand side of this number x, which is the largest integer, and it is not greater than this minus 2.3. So in that case it is minus 3. So when we have a negative number, we have to choose always on the this side, left hand side. So m, that is 1 upon epsilon plus 1 box value, is always some integer which is always not greater than this 1 upon epsilon plus 1. Okay, and that means this m is always greater than 1 upon epsilon, because it is 1 upon epsilon plus something positive. So what happens if I choose my m to be this integer? Okay, there are two things happens. One is m is greater than 1 upon epsilon, and also because of this box function, this m is a positive integer, because 1 upon epsilon is positive and 1 is also positive, so this is finally a positive number. So m value is always greater than or equal to 1. M is not only greater than 1 upon epsilon, m is also greater than or equal to 1. Okay, so what we can say here is, if I choose n, the term number n greater than the number m, which is given by this, then what happens is mod of an minus a, that is mod of 1 upon n minus 0, which is nothing but 1 upon n. Okay, we'll get 1 upon n. And 1 upon n, I can write less than 1 upon n, because we have chosen n to be greater than m. Or I can write, if I choose n greater than or equal to m, then 1 upon n is less than or equal to 1 upon m. So for n greater than or equal to m, I can write 1 upon n is less than or equal to 1 upon m. But 1 upon m, because of this condition, by our choice of the number m is this, so m is greater than 1 upon epsilon. So 1 upon m is less than epsilon. So this is less than epsilon because m is greater than 1 upon epsilon, implies 1 upon m is less than epsilon. So this suggests that if you choose your term number n greater than or equal to this value m, which is a positive integer, then the difference between an and a can be made less than epsilon. So this suggests that given any epsilon, you can always, if you can choose a number n such that this happens, then we say that this a is the limit of the sequence an. So in this case, we say, therefore we say that as n goes to infinity, or n becomes very, very large, the approach of the given sequence an is to the number a, which is 0 in this case. So using this concept and discussion, now we are in a position to define the meaning of limit of a sequence mathematically. So let us write down the definition of limit of a sequence. Limit of a sequence. Okay. So let an be a sequence of real numbers. A sequence of real numbers. And A belongs to R. A is some fixed real number. If for every epsilon greater than 0, if for every epsilon greater than 0, there exists some positive integer m such that for all n greater than or equal to m, for all n greater than or equal to m, if mod of an minus a is less than epsilon, then we say that as n tends to infinity, the limit of the sequence an is a. Then we say that as n goes to infinity, which we write in this way, n tends to infinity, the limit of the sequence an is the number a. And this we write symbolically. It is in this way. It is denoted by limit n tends to infinity an is equal to a, or we can also write as limit an is equal to a. So before we proceed, we want to understand this condition in more detail. Say, given a sequence an, and if you know some number a for which this condition is satisfied, then the number a is called limit of the sequence an. That's what this definition means. So this means also that if you do not know the value of a, you cannot check this condition. In other words, the definition of limit cannot be used to find the value of a. If you already have a sequence an and the number a, then you can check whether that number a satisfies this condition, or that number a is the limit of this sequence an or not. Okay. And the meaning of mod of an minus a less than epsilon for all n greater than or equal to m, we want to understand in more detail as follows. You know that mod of an minus a is less than epsilon, means a minus epsilon less than an less than a plus epsilon. You know that condition, mod of x minus a less than delta, if and only if a minus delta less than x less than a plus delta. So we are using that inequality. And this also means that an belongs to the open interval a minus epsilon comma a plus epsilon. So this condition says for every n greater than or equal to m, this an belongs to a minus epsilon comma a plus epsilon. So we understand this statement using a diagram. So consider a number line, say this, and suppose the number a is somewhere here, and for any given epsilon we consider a neighborhood a minus epsilon and a plus epsilon of the point a. This epsilon is very, very small, and this is our number line. And this condition says after m onwards, for every n greater than or equal to m, the term an belongs to this open interval. It belongs to this open interval. Means, suppose for simplicity, suppose m is equal to say 25, then after 25th term onwards, all terms falls in this interval. So if we have say a1 somewhere here, a2, a3 and so on, say a24, but for 25th term onwards, the a25 and a26, all terms fall in this this interval, and therefore the distance between this an and a will be less than epsilon, as all elements after 25th onwards. So A25, A26, everything belongs to this. So the distance between A and that all terms will be less than the number epsilon. So in short, if you find some number A, so whatever small neighborhood of this point A you choose, if you can accommodate infinitely many points except few points, then that sequence is said to be said to have a limit A, or it's said to converge to the point A. Okay, so that is very important thing. And if limit of the sequence an exists and it is equal to some real number, then the sequence an is said to be a convergent sequence. So let us define what is convergent sequence. So another definition, a very simple one. If limit n tends to infinity, an is equal to, say, A exists for a given sequence, then the sequence an is said to be convergent. Is said to be convergent. Otherwise, the sequence an is called divergent sequence. Otherwise, it is called divergent sequence. It is called divergent sequence. Now let us recall some important limit of some sequences which are useful in convergence and divergence of infinite series. So let us recall. The first one is, which we already proved in our discussion, that limit as n tends to infinity, 1 upon n is equal to 0. And the second result is limit n tends to infinity, 1 upon n raised to k is equal to 0 if k is positive. If k is positive. Number 3, another useful result, limit n tends to infinity, nth root of n is 1. Here nth root of n, or you can write this way also, limit n tends to infinity, n raised to 1 upon n is equal to 1. Then number 4, limit n tends to infinity, a raised to 1 upon n is equal to 1. A raised to 1 upon n is equal to 1, where a is any positive real number. A is any positive real number. Okay. Then number 5 is limit n tends to infinity, r raised to n is equal to 0 if mod of r is less than 1. That is minus 1 less than r less than plus 1. You just observe that this r raised to n is nothing but our geometric sequence. The terms of this sequence are this r raised to n, let me write here, r raised to n is actually this sequence r, r square, r cube, and so on. So the ratio of two consecutive terms is r square by r is r cube by r square is also r. And you know this very famous result that the geometric sequence converges to 0, its limit is 0 if the ratio r lies between minus 1 and 1, that is mod of r is less than 1. So very, very, very important result. And another thing is another famous sequence, limit n tends to infinity, 1 plus 1 upon n whole raised to n is equal to the constant e, where you know what is the number e, its value is 2.7181 and so on. And the interesting thing about this sequence that you can take here as the sequence an in this case is the sequence of rational numbers. 1 plus 1 upon n raised to n. If you put n equal to 1, 2, 3, and so on, then all the terms of this sequence are nothing but rational numbers. Means the number of the form a upon b, where a and b are integers and b is a non-zero integer. So all numbers of, or all terms of the sequence are rational numbers. But the limit of this sequence, this rational sequence, is the number e, which is an irrational number. So that is very, very useful. Okay. Another very important result about limit of a sequence is the following theorems, which we assume that if sequence an is convergent, I will always write convergent in short form as CGT, convergent, then the sequence an is always bounded. So every convergent sequence is bounded, means all terms of that sequence will be lying between some two constants. Another very, very important theorem which is useful for discussion of convergence and divergence of series, if a sequence an is monotonically increasing and bounded above, then the sequence an is convergent. Now monotonically increasing means, every term is say less than the next term. So an less than n plus 1 or n less than or equal to n plus 1 is called increasing sequence condition. And bounded above means all terms of the sequence are less than or equal to some constant or some real number. So that is called bounded above. And if a sequence has these two properties, it is increasing and bounded above, then it is always convergent, means the limit of such a sequence always exists. And we have a similar result about decreasing and bounded below sequence. If a sequence an is monotonically decreasing sequence and it is bounded below, then also the sequence an is convergent. So every monotonically decreasing sequence and which is bounded below by some number is always has a limit. Okay, and this two we can combine, that if a sequence is bounded, it may be bounded above and below, and monotonic, either increasing or decreasing, is always convergent. So another very, very important result. All these results we have proved in the course of analysis. So just we are mentioning which are useful in our discussion of convergence and divergence of series. So let an, or let me write directly, every monotonic and bounded sequence, of real numbers is always convergent. Means a sequence is monotonic, so it is either increasing or decreasing. Suppose it is increasing, and we are also given that it is a bounded sequence, means it has both upper bound as well as lower bound. So it is bounded below as well as bounded above. If a sequence is bounded, then if it is increasing, then also convergent, or decreasing, then also convergent. So this theorem follows from theorem 2 and theorem 3, where the condition here is it should be a bounded sequence. So this is also very, very useful theorem, which we are going to apply at many places in the discussion of convergence and divergence of series. Okay, so in these two videos, we have discussed sequence, limit of a sequence, and some important results which you just remember. And this is not the main part of our topic of convergence and divergence. These are all prerequisites. So in the next video, we are going to start our main topic of convergence and divergence of infinite series. So first we'll introduce what is the series and then understand what is the meaning of convergent and divergence series. So thank you.